This diagram shows a common trap in computer science, trying to measure an algorithm's speed with a stopwatch. Because hardware speeds vary wildly, a faster computer running a terrible algorithm might beat a slow computer running a great one. So instead of timing seconds, we count the discrete mathematical operations the algorithm performs. When we chart how the number of those operations grows as our input size, represented by n, increases, we are measuring time complexity. If you have 5 data entries, a process might take 5 operations. Scale that to 100 entries, and you watch the operation count scale identically. But counting operations is only half the equation. We also have to calculate space complexity, which is the total physical memory required by the algorithm. As your input size grows, we measure exactly how many storage cells light up to hold the incoming data. Evaluating any algorithm requires weighing these two metrics against each other. Engineers often have to choose between a solution that executes rapidly and one that respects strict memory limits, a balancing act known as the time-space trade-off. This coordinate graph maps common algorithmic time complexities, showing exactly where greedy algorithms usually land. Most greedy solutions start by sorting data, rather than testing every possible combination. Because of this, they often sit right here on the highly efficient O of n log n curve, powering established methods like Kruskal's or Huffman coding. This operational speed comes directly from their core logic. At every step, a greedy algorithm makes an immediate choice based on a simple rule, like constantly picking the maximum available value. It ignores alternative routes entirely, keeping it incredibly fast, easy to code, and light on memory. Let's look at this coin selection scenario to see the fatal flaw in that speed. If we need a specific target value, the greedy path immediately grabs the largest coin possible. That rigid rule forces it into a corner, and it requires 3 coins total to finish the job. A smarter path ignores that initial large coin and hits the exact target using only 2. Because greedy algorithms cannot backtrack to correct a bad choice, their mistakes are permanent. Knowing that greedy algorithms can lock themselves into permanent mathematical errors means we cannot trust them universally. They are only reliable for highly specific challenges, known as optimization problems. An optimization problem requires you to search for the absolute best possible outcome among many competing choices. You are trying to maximize profit, minimize cost, or find the shortest physical distance, all while operating under strict limits. This visual represents the ultimate test case for algorithmic decision-making, the knapsack problem. The tension is straightforward. You want to maximize the value of the items you place inside this bag, but you absolutely cannot exceed that strict 20-kilogram weight limit. Let's scale this into a practical scenario, like packing for a Mount Everest expedition. We have a set of available items. Each has a specific physical weight, and each carries a distinct level of importance to your survival. Take a look at these values. If your bag can hold exactly 10 kilograms, which combination of items would you choose to maximize your survival importance without breaking the limit? Your approach to solving that depends entirely on the physical nature of the items. Here we see a gold bar cleanly sliced in half by a laser. This is the fractional variation, where items can be divided. Contrast that with a laptop. You cannot pack half a laptop. It is an all-or-nothing choice, defining the 0-1 knapsack variation. That simple physical constraint, whether an item is divisible or indivisible, dictates exactly which algorithm is mathematically capable of calculating the right answer. To apply a greedy approach to the fractional knapsack, we build our goal into a formal mathematical equation. Our objective is to maximize the total sum of our profit, strictly subject to keeping the sum of the weight below our total capacity. The secret to satisfying this constraint isn't looking at the total weight or the total profit of an individual item. The greedy strategy evaluates items entirely on their profit per unit weight ratio, isolating the highest possible value per kilogram. Let's organize the 4 pillars we have built. We measure algorithmic efficiency through operations and memory. We know greedy logic is lightning fast, but rigidly permanent. We know those traits limit it to optimization problems. And finally, we know the knapsack problem splits into divisible and indivisible item constraints. When we specifically target the fractional knapsack, calculating that profit-to-weight ratio mathematically guarantees the greedy algorithm will find the perfect answer. In our next step, we will break down the precise numerical mechanics of that winning algorithm.